So here's the latest batch of PCBs that just arrived from JLCPCB, and as you can see, this looks very similar to the PCB we made together in the tutorial video, which you can see on my channel. Pretty much the centerpiece is an STM32 microcontroller, an STM32F405 with floating point unit to be precise. And I've added a few more different components to this board just to make it a tiny bit more interesting so we can have a play around with software and actually writing drivers and stuff like that for it. You can see some of the components haven't been soldered on yet because JLCPCB doesn't support 3-hole components, for example, and some connectors. So I'm going to have to add those myself, which I'll do later. But let's talk about what else is actually on this board. So we have a USB connector, which I'll put on here, a power connector, and various connectors on the outside as well, just to interface with the STM32 microcontroller. The power, either 5 volts from the USB or up to about 12 volts on this power connector here, goes to the buck regulator, which steps it down to 3.3 volts, which feeds the remaining part of the board. So we have a high-speed external crystal over here, and we have the first interesting chip over here. This tiny one here is an inertial measurement unit by Bosch. It's a BMI 088, and it interfaces with the STM32 microcontroller via SPI. So that's an accelerometer and gyroscope in one package. Here we have a 1 gigabit size flash memory, which also interfaces with the STM32 via SPI. And up here, it's quite hard to see and quite small. It's either a Bosch BMP 280 barometric pressure sensor, or in this case, I've used a cheaper alternative, which is the SPL06, but it's the same thing. Via SPI again, relays the data, pressure data to the MCU. Other things I've added are this RGB LED, so red, green, and blue, which I've connected to 3 timer channels on the STM32, so we can control that via, or the brightness rather, via PWM. I've also added a serial wire debug connector up here, and a boot mode select switch. And that's pretty much all there is to this board. Nothing too crazy or fancy, but it lets us test out a few different peripherals and see how we can interface them, and see how we can actually program this STM32 microcontroller, which is going to be the main part of this video. But as you can see, I just wanted to show you the kind of soldering and assembly results from JLCPCB. I'm using really tiny components. All the smallest ones you see here are 0402. So it looks really neat, I think. So it came out pretty well. I'll just show you the backside as well. There's nothing too crazy on the backside. You can see all the vias. I've added some silk screw and some indicators where the ground and positive terminals are. And that's pretty much it. So very similar to the board we designed together in the tutorial, but I've just added some more interesting components. I'll put the Gerber files and the assembly files in the description, and I'll also show you how to order this board so you can essentially play along at home. So as you can see here, I've added these 3 components which weren't assembled by JLCPCB. One of them is the boot mode select switch, so I can select between run and boot. Essentially that just pulls the boot 0 pin high or low. I've added a serial wire debug connector up here, which is a 10 pin 1.27mm pitch connector, and I've added this micro USB connector up here. And that's pretty much all we need. We're going to use this essentially to power the board and to relay data, kind of like a virtual COM port. This to program the device, and this essentially to put it into run or boot mode. So here I am at my desk now, and the first thing I typically do when I have a new board and I've just soldered on some additional parts is to make sure I haven't created any shorts, or there aren't any shorts from the assembly process. And then I apply a voltage to the power pins, slowly ramp up the voltage and see if the current drawn is what I would expect. If the current drawn is too high, you probably got a short somewhere, and so on. And then I just make sure all the voltages on the board are what they should be. And from that, I can then actually connect it to my ST-Link and via USB connector to my computer. But before that, just make sure all the voltages and currents are in order, just to make sure you're not going to fry anything. Okay, so what you need is an ST-Link. I've got this, I think, version 2 over here, with an adapter cable to one of these mini connectors. And I also have a micro USB cable, which is going to hook into my computer. So all you have to do is fit that onto the debug connector, and then plug in the micro USB, and with any luck things will kind of turn on. So I've got this green LED here, which is kind of my power good LED. This is for the 3 volt buck regulator, and the LED, the RGB LED has lit up as well because I've really played around a bit with the firmware. But now let's have a look at the computer and see how we can write drivers and the software for this board. Before we get started, let me just show you how to order these boards with JLCPCB, including assembly, in case you'd like to try these out for yourself at home and just kind of follow along. So first thing you need to do is go to my GitHub repository, under this link, github/bms67. Then click on repositories, and it should be here in Little Brain STM3204 sensor board. And I've put all the things you need here. So first of all, the Gerber files, just to get the PCB produced. And in the assembly folder, the bill of materials and the footprint position files. And that's what I use to order my boards as well. So once you have those, you can either clone the repository or just download it. Go to JLCPCB and click on Quote Now. Then in the Gerber folder in the GitHub repository, just upload the raw file. So once the board files have uploaded, you can see a little preview here. You can also check out the Gerber viewer. It's a 4-layer board, 55 by 55 millimeters. So let's just order 5 for now. Impedance, we want impedance control for the USB traces. I typically go with lead-free hot air surface leveling or ENIG. All of this is fine. I've also hidden the order number under the chip, so that's why you can click on specify location. We want SMT assembly. We want the top side assembled, 5 parts, and I've already added the tooling holes. We can agree and click confirm. Click add bill of materials. Navigate to the assembly folder and upload bill of materials. Same thing for the footprint position files. Once you're happy with that, click next. So click on next. I've already adjusted the footprint rotations just to make sure everything's kind of correct. So you can see some of the parts aren't available just now, but I'm sure they'll be available soon, and then you can just order the board. For this video, I'm going to be using the STM32CubeIDE development environment, which you can download for free from ST's website. Now, there's loads of different development environments you could use, for example, Embed, or these IDEs such as Keel and Atolic. But I prefer this because everything's really nice and integrated, all the pinouts are there, a lot of the low-level drivers are already written, and that's what I typically go for. And I'll also be using C in this video. You could also use C++, but for my needs, C is all I need. And that's essentially down to your personal choice. There's also a thing with STM32 called the hardware abstraction layer, or HAL for short, and that's kind of ST's help to write a lot of the low-level drivers and low-level interfaces. Instead of you having to mess around with registers and so on the chip, you can use this HAL. Now, the HAL is oftentimes kind of bloaty in terms of code it adds, and a lot of times it can also be quite buggy. So just be careful when using the hardware abstraction layer. But for something as simple as this and just testing the board and making sure things work, this is completely fine. So without further ado, let's get started with STM32CubeIDE. So here we are on STM32CubeIDE, and the first thing we want to do is start a new project. So click on File, New, STM32 Project. This will initialize this target selector, and this is where you type in essentially what board or what chip you're going to be using. So you can either use one of these development boards or discovery boards, but what we'll be doing for our custom board is typing in the MCU number. So it's an STM32F405RG. This will appear in this list down here. You can check it's the right package and the right chip, then select it and click Next. Now we need to enter a project name. So I'm just going to be calling it Little Brain Firmware. You can put it in a different location if you want. I'm going to be using C, and you can all leave this as it is. Click Next. You can choose which firmware package you're going to be using for the hardware extraction layer, but always just use the latest one, I would say. Click on Finish, and it'll start creating some code. But the next thing we need to do is actually do the pin assignment for this chip. So this pinout view will open, and this will enable us to choose peripherals and select pinouts for the chip. So we can either click on the individual pins and see what functions they may have, or we can use this toolbar on the left. So the first thing we need to enable is the debug. So we're going to be using serial wire debug. So click on System Core, Sys, Debug, and we want serial wire, but we also want the SWO trace, which is then you have to click here. So SWO means we can do printf via the debugger, for example. So click on that, and you can see in the right view here, it's actually enabled the data pin, the clock pin, and the serial wire trace. Next thing we want is the external high-speed crystal, and that's under RCC. High-speed crystal, and click Crystal Ceramic Resonator. And this will enable these two pins over here. So that's pretty much all the essentials, which I always start with, so the high-speed crystal and the serial wire debug. The next thing we need to do is actually enable the peripherals, and that depends on, of course, the board as well. So we might want SPI, we might want a couple of timers, we want USB, and so on. The way I typically do that is I will have my project in KiCad, which will also be in the GitHub repository. And here you can see the pinout for my hardware. So we've already added the crystal, we've added some of the serial wire debug stuff, but now we need to add the connections to the different peripherals. And we'll just be testing, for example, the inertial measurement unit, which is an SPI, we'll be testing the USB, and we'll be testing the RGB LED for this video, which are these 3 timer channels. So all you have to do is transfer what you need over to STM32CubeIDE. So let's do that quickly. So the first thing I need is USB, and I'm using USB full speed. It's going to be a device only, and this will enable pins PA11 and PA12, so the data plus and data minus. Okay, the next thing we need is the SPI1, which is somewhere down here. So we want a full duplex master because we want to be able to receive and transmit at the same time. And these pins are enabled. So you can either use a hardware chip select signal as an output, if it's a master, or just assign GPIO outputs and just do the chip select in software. And that's what we're going to be doing. So we have 2 chip selects because we have an accelerometer and a gyroscope. PA4, I just click on it and select GPIO output. PC4, I select and click GPIO output. If you right click on one of these, you can enter a user label. That's kind of useful. So I want to call it accelerometer _ chip select. Actually, it should be NCS because it's inverted logic. And for PC4, this is the gyroscope chip select. Okay, so we've set up the crystal, we set up the debug, we set up USB, and we've set up SPI. I would also like 3 timers because we're going to be using timers to control the RGB LED intensity via PWM. And I believe my timers should be up here. So I have timer 3 channel 1, timer 3 channel 2, and timer 4 channel 1. So this is the RGB channels for my LED. As you can see, they're yellow. We should always enable them over here. So go to timer 3. We want to choose the clock source as internal clock. Channel 1, we want PWM generation. Channel 2, we also want PWM generation. Let's do something similar for timer 4, which is this third one here. We select the internal clock, and we choose channel 1 is PWM generation. Now, this is pretty much it so far. There are some things we have to change. For example, we want to select the PWM frequency, we want to select the baud rate for the SPI. But before we can do that, you might notice up here I have this little cross, and this means that there's some error or problem with the clock configuration. So let's click on that. It'll tell you to, if you want to run automatic clock solver, we don't want to do that just yet because we have to change some values. So first thing we want to do is, I've chosen a 16 megahertz crystal. So I will type that in here, 16. As my PLL source, I want to use the high-speed external crystal, not the internal one. Then I also want to run my system at the maximum clock frequency, which STM32CubeIDE tells me is at 168 megahertz. So I type that in. Now I want to run the automatic clock issue solver to make sure all these PLL values are correct. So just click enter. Click OK. It'll try and figure out a solution, and it has. So we have no more cross up here. Everything looks fine. We've chosen our 16 megahertz high-speed external crystal, and we've chosen the maximum system frequency. And STM32CubeIDE has set up all of our clocks and routing for us, which is really nice. So we can go back to pinout and configuration, and now we can actually set up the baud rate and stuff like that. One thing I would also like to do for the USB part is I want to be using this to relay data back to the host computer. So I want to have essentially a virtual communications port. Luckily, there's a driver for that for ST already. If you go down here, middleware, USB device, and choose a class. So you could have, for example, an audio class, if you want a mass storage class, some sort of human interface. But what we want is this communication device class, virtual COM port. Click on that, and that makes sure when we create the remaining files for this project, we include the drivers for that as well. Okay, so let's look at the SPI to change the baud rate. You can always see down here we have these various tabs if we want to use DMA and so on. But for now, we just want to look at the parameter settings. You can choose the frame format, data size, if we want MSB or LSB first. But what's interesting at the moment is we want to change the baud rate. As you can see, the baud rate right now with these clock configurations is at 42 megabits per second. And that's rather too fast. we want something at max maybe 12 megabits for the most cases. So the way you do that is change the prescaler, and let's set that maybe to 8 for now. And you can see that has now changed the baud rate to 10.5 megabits per second, and that's plenty fast for our purposes. A bit more complicated now is the setup for the timers. All right, we want to generate PWM, which then drives the LED. So let's look at timer 3, and we'll copy those settings then to timer 4. The important things for PWM are effectively the prescaler and the counter period. Now we have some sort of input clock frequency. We want to scale that down using the prescaler and then the counter period to give us essentially 100 Hertz. The question is, what is the source clock frequency? Which one of these is the source clock frequency? And again, look at the datasheet. This is the STM32F405 datasheet, and section 2.2, we can see down here, timer 3 and timer 4 are connected to the APB1 bus. Go back to CubeIDE. APB1 bus is over here and nominally running at 42 megahertz, but the timers are connected, or rather doubled, at 84 megahertz. Okay, so from the datasheet we can see what the timers are connected to. So we want to scale down 84 megahertz down to 100 hertz. The way we can do that is 84 times 10 to the 6 divided by 8400 gives us 10,000. 10,000 divided by 100 gives us 10 hertz. Okay, so we scale down 84 megahertz to 10,000 to 100 hertz. Okay, we also need to subtract 1 from both of these, because there's some small quirk that actually these prescaler and counter period values will be added 1 to later. So always, I either do it explicitly by just subtracting 1, or just write 8399 and 99. Okay, and we need to do the same settings for timer 4, because it's on the same bus. So we do 8400 and 100. And all of the remaining settings here, I believe, are pretty much fine. We're not doing anything flashy, just PWM running at 100 Hz with a counter period of 100. Okay, I think that's pretty much it. We set up the timers, we set up the debug, we set up the USB with the communications device class, we set up the SPI, the baud rate, the software chip select signals, and the high-speed external crystal. And that's pretty much it. All that's left to do is now click on Save. Once you click on Save, STM32CubeIDE will generate all of the low-level drivers for you, which is really nice. So once it's finished, go to the core folder, source folder, and click on main.c. And you can see here, all of these things have been created. So it's created all the handles for the SPI, for the timer, it's created initialization functions, and our main function block, right? So basically, you could start and just write code in here, and everything would kind of work. Okay, but let's look at the RGB LED first. So I've cleaned up the code a tiny bit. I've just removed all the comments from ST. Now they have a purpose because ST will tell you where you can put your own code without it being deleted every time you make a change in this file. But for now, I've just cleaned it up just to make sure we can see things a bit easier. So we're going to start off with the RGB LED. And for that, let's just have a look on KiCad again, how it's hooked up. So you can see this is the RGB package in the schematic, and it's actually hooked up to 3.3 volts. And the GPIO outputs are essentially sinks. So when the outputs are low, the LED will turn on, and when the outputs are high, the LED will turn off. So it's kind of inverted PWM, let's just call it. So let's just keep that in mind. Okay, but the first thing we need to do is, before we get into the while loop, is actually start the PWM timers. So we can do that by using a hardware abstraction layer, and there's a function called howltim PWM start. We then need to pass it essentially which instance or which time we want to use. In this case, we want to use the first channel of H timer 3. So we then type in we want to start the first channel. And we would do that the same thing for timer 3 channel 2 and then timer 4 channel 1. Okay. The way we then set the intensity is by modifying a property of this struct HTIM3, and we'll do that in the main while loop. But let's essentially just make a program that then increases the intensity until it hits the maximum and then resets. So for that, let's create an 8-bit unsigned integer called intensity and start it off at 0. Then in the while loop, let's say we want to set the intensity. So whatever this variable holds, we want to set the intensity or the PWM duty cycle of the output. And the way we do that is we access the struct and essentially want to access this register, CCR1. And that'll then essentially set the counter period for how long it is on. And that in turn will be our duty cycle because we had set 100 Hertz. The counter period is 100. So that'll be our duty cycle. Remember, we could just say it's equal to intensity, but I said before it's essentially inverted. So we want to invert that by saying it's 100, so the maximum duty cycle minus the intensity. Then every loop iteration, we want to increase the intensity, and if the intensity is essentially above the maximum value, we want to reset it, right? Because we can run from 0 to 100, but as soon as it's above 100, we need to reset the intensity, because otherwise it's the wrong value. Now, if we just were to run this, we wouldn't be able to see a difference, because this is running essentially the maximum speed this while loop can execute. So the delay function with the hardware abstraction layer is called how_delay, and that's in milliseconds. So let's say we want 100 milliseconds delay between each change, right? So to start, we started the timer in PWM mode. We're using a variable to store the intensity, and in the main while loop, we're setting the intensity using registers, right? And just making sure the intensity is in valid ranges, and then setting delay. So let's check if this code is correct. We can use that using the build, this little hammer up here. And we see, 0 errors, 0 warnings. Perfect. So the next thing we want to do is actually debug and send it to our microcontroller. So I've hooked everything up with zero-wire debug, and I've got power to the board. Then I can click this bug icon. And then we need to create a debug configuration. And pretty much the default settings are fine. The interesting settings are in this debugger tab here. You can choose if you want to connect to a particular ST-Link, what type of server you want to create, how you want to connect to it, if it's under hardware reset, software reset, if you want to enable the trace output. But for now, let's just keep everything as it is and just click OK. You can see it's going to start the launch. It's going to connect to the debugger down here. You can see, it's recognized the device. Let me just scroll up again. It's recognized the device. It's of this family. It tells you what flash size it is, and so on. So it looks like everything's working well on our board, and it's connected. It's uploaded the memory, and now it's ready to run. By default, it always puts a breakpoint at the first line of main. So right now it's paused, so you can see here. So to start the program, we click on resume. And now I can see, I'll show you in a second, I'll switch the camera. And now the red LED is going and increasing in brightness. So let me just show you that now. So as you can see, the red LED is going from 0 intensity to maximum intensity. And you can see the ST probe is doing its thing as well. So that seems to be working. I've added these two functions to the main C file just to clean things up a tiny bit. Ideally, you would put these all in separate C and .h files and make this into a proper little project. But for our purposes, we just want to test the board. So I've made two RGB LED functions. One is to initialize. So we had the timer start functions, and I'm doing that for timer 3, channel 1 and channel 2, as well as for timer 4, channel 1. Right, so we don't have to always just write that in the main file. And then I just call this function LED RGB init, and that'll then call all of that. The second function is just to set the intensity of the red, green, and blue channels. So I pass red, green, and blue as arguments, and then I just set the registers. So CCR1 is for the first channel, and CCR2 is for the second channel of the relevant timer instance. Yeah, so it's pretty simple, just clean it up a tiny bit. And then I can just call the set intensity function, and for now I've just let it all be equal. So now I have essentially white light because all the intensities are equal. Okay, so let's move on to the next thing, which will be USB. So I've cleared up some of this LED RGB code over here in this while loop, just so we can focus on USB for now. Remember in the pinout file, we already configured USB, and we also added the drivers for the CDC virtual COM port. And we're going to be using this virtual COM port to relay data back to the host computer. So we can look at it via HTerm, or PuTTY, or any program you use. Or for later, if you want to develop your own applications, you can just log and debug data. So it's already included USB device.h, but we also need to include another file, which I find rather strange that doesn't include automatically. So this is one of the files that's already available and linked in the system. So it's USBD underscore CDC underscore IF. And this is needed for a particular function we're going to use to transmit essentially a string of characters. Okay. So we have that included, that's important. Now let's just create, for example, a buffer. A character buffer where we can send, I know, let's say numbers running from 1 to 100. So I'm just going to give it some ample space. I don't know, I mean 8 is probably far too many characters, but just a buffer that can store the information we want to send. I'll also just put in a counter, counting essentially from, let's say 1 to 100. So we start the count at 1. And now we're in the main while loop. So on every iteration, we want to essentially set the transmit buffer characters. So I use sprintf for that. That's probably more elegant ways, but it's really simple to do that way. And in the buffer, I would like to put an unsigned integer, so %u, and a carriage return new line. And in that unsigned integer, I want to put count. So this is standard C syntax, right? Sprintf, I can fill this into the buffer with the variables here. That's all I'm doing. So I'm filling the character buffer, which will then transmit via USB, and I'm incrementing the count. I'm also checking the count. If it's larger than 100, I would like to reset it back to 1. Okay. Now comes the important part. So now we want to transmit whatever's in this TX buffer via the virtual COM port. And the command for that is, or the function rather, is CDC underscore transmit underscore FS, so for full speed. Now it's character, which is pretty much almost equivalent to uint8, but we still need to cast it, otherwise STM32CubeIDE will complain. So we cast it to a pointer of uint8 type, and I'm just going to use the string command to tell this function how many characters we want to transmit. So it's a really simple function. This is the name. We want to transmit a character buffer or array of this length, and that's all we need to do. And so then we just wait a tenth of a second and transmit it. So click on build. With any luck, this should compile. And then we can pretty much just, so you can either click on debug and then step through the program, or if you just want to have it run immediately, you can click on this run button without any debugging. So let's do that now. Okay. So it's connected to the serial debug. It's going to start uploading now. Okay, I'll upload it and it's done. As you can see, there's no pause button because it's just running on the microcontroller now. So if I go to my device manager, you can see it's now enumerated in my ports list. So it's enumerated as a STM virtual COM port, and it's under COM5. So let's see what happens if we now try and connect to that. So I'm using HTerm. I'm choosing my port, COM5, and the baud rate doesn't matter. This is now USB, it isn't UART or anything. So just click connect, and you see we get this error down here, and it says it can't connect. The problem with STM32 or with uploading code which has to do with USB is the enumeration. And the way you can just get around that is by plugging in the USB cable, and then it should work. So let me just do that. So I'm unplugging it now, and I'm plugging it back in. Let's give it a couple of seconds and I can click connect. And as you can see, here the number's now being listed. All right. So it'll go through past 100 or at 100 and then loop back around. So exactly the code we have here. And this is going via the USB cable. So that's pretty neat. Okay. And of course you can make this probably quite a bit neater, right? You could try and root printf to do this so you don't have to do all this sprintf stuff. Or we could make something that checks if bytes are still being transmitted to USB and make sure that you're not transmitting when it's already transmitting something, and so on. So, but this is just the idea that it's actually fairly straightforward to implement a USB communications protocol. Okay, so the next thing is let's implement the driver for the SPI device, or one of the SPI devices, and that is the BMI 088. So the driver we'll be writing is for the BMI 088, which is 3-axis gyroscope and 3-axis accelerometer in one single package. And we can either interface via SPI or I2C, and I've chosen SPI. So we're going to write a really, really simple SPI driver, just so you can see how you might approach this. And it's going to be polling, so nothing like DMA or with interrupts, really the really simplest and, in effect, kind of worst type of driver you could write for SPI, because polling mode essentially takes away from your processing power from the MCU. But it's the quickest way to test a driver. You don't have to worry about DMAs, any sort of buffers or anything. it's really simple to test. And that's what this whole purpose of this video is, to test drivers and test this board. Okay, so when we're writing device drivers, we always want to look at the datasheet. And this is a fairly long 50-page datasheet, but it tells us everything about what registers there are, how we can read from registers, how we can set up interrupts, how we can set parameters of this, and how the protocol generally works, what kind of bytes it expects, and how we read and write to it. So section 6.1 of the BMI 088 datasheet details the serial peripheral interface, or SPI, and that's what we're going to be using. So there's a lot to read through, but in essence, both the accelerometer and gyroscope share the same main SPI pins, so MOSI, MISO, and SCK, so the clock, but they each have different chip select bits, and that's how you interface with the sensors. And the interfacing with each of these parts, accelerometer and gyroscope, is slightly different. And we can read that over here in 6.1 and 6.1.2, I believe. Yep. So for the gyroscope part, this is effectively telling us how we read and write. So we send 1 byte, that's the address, and depending if the first bit, so the most significant bit, is either 0 or 1, we either write, or when it's a 1, we read. Right? So we send the register address with either 1 or 0 in the most significant bit. That tells it to read or write. And after that, the device then sends us the contents of that register, or we write the contents to that register. So really simple. The accelerometer is similar, but after the first address byte, the accelerometer sends a dummy byte, and then only the true data. Right? So when in read mode, these bits contain unpredicted values. So it sends a dummy byte, and then it sends the true data. So this is a kind of a 3-byte cycle for the accelerometer, and there's a 2-byte cycle for the gyroscope. But we'll see how to implement that. So I've written a very simple gyroscope read function and very simple gyroscope write function, and they either write or read to or from the register, 1 byte. Okay, so let's briefly go over how they work. They take one of the arguments they take is the register address, so from which register do we want to read? And here we take a pointer to where we want to store the contents of that register. This function either returns a 0 if the read failed, or a 1 if the read succeeded. Okay, now from the datasheet we saw that we have to read a byte, we have to send the register address, and we have to flip the most significant bit to a 1. And this is how we do it. So we OR the address of the register with the bit mask of 1 followed by 7 zeros, which in hexadecimal is 80. Okay, you'll see in a second why we need to send a second byte, but this is pretty much just taken from the register. Now with the generic SPI read or write, you can also find this in the register, we want to pull the chip select line low. This is how we do it with this command. So there's the HAL GPIO write pin, and we say which bank it is, what the pin name is, and we say we want to put it low. Then we do our transaction, which we'll look at in just a second, and then we pull the chip select line high again. Okay. So our transaction is how SPI transmit receive. And we can only do this because we're using a full duplex SPI. So we can transmit and receive at the same time, which will save time overall. The problem is we now need to send 2 bytes of data. We first will send the register address with the most significant bit flipped to 1, and then we need to send a byte of dummy data. We need to send a byte of dummy data, otherwise this transaction won't work and there won't be anything read. So while we read, we also have to write, and vice versa. Okay? But the most significant part, or the most important part, is here, and then we just send a byte of dummy data. So actually, the register contents will then be in the second byte of this RX buffer. Okay, so we pass the handle, which is HSPI1, which you can see up here. So we've passed which SPI do you want to use. We say the transmit buffer, the receive buffer, and how many bytes of data you want to use, and what timeout we want to have. Okay. And this function will return HAL OK if the transaction succeeded, or HAL busy or HAL error if it didn't work. And then we indicate this by the status bit, which we then return. So if the status is 0, then it didn't work. If the status is 1, it did work. So after this hopefully went well, we then put the data of the buffer, the second byte, into this memory location here. And this is then will be the register contents. Yeah, so it's actually pretty straightforward. Essentially pull the chip select low, do the transaction, transmit, receive, and then pull the chip select high and return the data. The write function down here functions very similar. Because it's a write function, we actually don't need to flip the most significant bit. All right, that can be 0. But then the second byte we want to write is actually the data. So we have address, and then we send the data. So what register we want to write to, and what do we want to put into that register. And then it's the same thing again, pull the chip select low. This time we're using transmit, and then we're pulling the chip select high again. So really, really easy. And we can do something similar for the accelerometer. But now let's just test this to see if we can read some data from the gyroscope. So if we take another look at the data sheet, we can see on this page in section 5.4, we actually have the register map. And the register map tells us what address a certain register has, what the name is, and what that register also contains. So something which is really useful to always do is just, for example, read the chip ID. So if you read the register at address 0, that chip ID should be OXOF. Let's try and read that. So let's go back to CubeIDE and let's just, I don't know, just read it in a loop, let's just say. So we need some place to store the results because we're going to be passing this by reference. And then we want to call the function we just wrote. So that's gyread8. The register address is 0, that's the chip ID address. And we want to pass that by reference. Okay, so we can save that. Just build. And then we'll actually have a look at the contents of this register by doing some breakpoints and using the debugger. So we click on debug, then to launch it and upload the firmware to the STM32. Okay, just wait until that loads. There we go. Okay, of course we have the first breakpoint here. All we want to do is just set a breakpoint directly after the read operation. So double click on the left side here, and that sets a breakpoint. And then we can just click resume. Okay, and we can see on the right here, the variable data, which is this one here, or we can hover on top of it, has the value 15. And the value 15 in decimal is OXF, or rather OXOF in hex, which is exactly what it should be, right? So the gyro chip ID is OXOF, and we've seen that using the debugger. So we didn't even have to print this via USB or something. Okay, so that's pretty much it. Now, of course, we have to package this and make this into actually a proper nice driver package, where that would be too long for this video. But I'll attach the code in the Git repo. So basically, but this is the basis. If we want to do a gyroscope read, a gyroscope write, we need these functions, and everything is in the datasheet. We do the same for the accelerometer. We figure out what settings we want for this gyroscope and accelerometer, and then we put that in a neat little header file and a .c file. So as a final test, I've kind of put everything together and refined some of the drivers a tiny bit. You see I've written a header file and actual proper driver for the BMI 088. I've also added callbacks because the BMI 088 has interrupts whenever there's data ready. And so whenever there's data ready, I'm actually going to read the accelerometer or read the gyroscope. And I've added the LED, I've added the USB logging and so on, just to combine everything we've looked at in this video. So I'm just going to be printing all the accelerometer data, all the gyroscope data to USB. I'm going to be changing the RGB LED colors and essentially reading from the gyroscope and just initializing and setting it up. And all of this will be available in the Git repo for you to check out. Okay, so let's just take a look at that with a different camera. When I move the board, how the values change. And then that's pretty much it for this video. So the program's been loaded onto this microcontroller, onto the board. You can see the LED is flashing away, doing its job. I don't have the debugger connected anymore. I've got the boot mode switch in run mode, so boot 0 is pulled low. And I've got just this USB cable providing power, and it's connected to my main computer over here. So as you can see in the device manager, it is enumerated as COM5. And let's see if that actually logs the data. So here in H term, I'm connecting to COM5. So as you can see, every pretty much half a second we have data being logged. So if the accelerometer values, so X, Y, Z, so Z should be about 9.81, which it is. If I move the board around, so if I just rotate the board, the values will change. So I've put it on its side. Now the X component is 9.81. Put it on the other side, it's minus 9.81. And yeah, so the gyroscopes are the three values on the right. And as you can see, as I'm rotating the board around, those values change as well. So that pretty much brings us to the end of this video. We saw how to actually interface with our custom little board, how to program this STM32 microcontroller, set up peripherals such as the high-speed external crystal and so on, how to trigger a PWM, RGB LED, how to talk to some SPI interfaces, and so forth. And also, of course, connect to USB and then print stuff over USB. So I hope you thought this video was useful. If you did, please leave a like, hit subscribe if you haven't already. And let me know if you have any comments, if you would like to see something in a future video, maybe some more programming tutorials. But thank you for watching, and until next time.